So the law of conservation of energy, it should be majestic. It should rumble in your belly. What is it? The poetic way to say it is when the Big Bang occurred, the amount of energy that was in the universe at that time has never changed. The amount of energy in the universe is constant. And sometimes you'll see it phrased that way. Now that's on the macroscopic universal scale. If you want me to zoom in, here's what it says. We cannot create or destroy energy. What was energy? The ability to do work. Okay? We can't make that out of nothing. We can't destroy it once we have it. All we can do is transform it from one type to another. And what this means is if we're looking at a closed system, and Tristan, a closed system is one that has no outside sources of energy. There's not a motor off screen adding energy in. It's not plugged into something adding energy in. The amount of energy you start and the amount of energy at the end must be the same. If you start out with 5,000 joules of energy, how much will you end up with? So if you start out with 5,000 joules of potential energy and you transform 2,000 joules into kinetic, how much is still left as potential? 3,000. Has to be. Yeah, it's got to go somewhere. The way you'll often hear me phrase this, Sierra, is the energy's got to come from somewhere. It's got to go somewhere. It just can't make it magically appear, and you can't make it magically vanish. So KE was my abbreviation for kinetic energy. PE was my abbreviation for gravitational potential energy. It says this: both the KE and the PE of a block freely sliding down the ramp are shown below at the bottom position. Right there. Dylan, in your head, what's my total energy?
75 joules.
How much energy will I have at any point in this system? That's the law of conservation of energy. So if I have 50 joules of kinetic motion energy, how much must there be for potential?
25.
How much kinetic do I... You know what? Better yet, let's start at the top. How much potential energy must I have started out with?
75.
And so now what we can already explain with this is why objects speed up as they fall. As you fall, what happens to your height? Gets bigger, smaller, or stays the same? And since potential energy was mgh, what happens to your potential energy? That energy has to go somewhere. Where does it go into? Kinetic. As you fall, you speed up. And it doesn't just have to be falling in free fall, which is all we've looked up until now, because work and energy are scalars and don't care about direction. It'll work down a ramp, which opens up a whole new branch of questions. Cole, those are longer blinks. You going to make it? Dylan, what goes right here then?
25.
Yep. What goes right here? You already answered. 25 joules. So in words, the law of conservation of energy, or I'll abbreviate it sometimes because I tend to abbreviate as C of E, says the amount of energy a closed system has never changes. As an equation, we could write stored energy initial plus motion energy initial equals stored energy final plus motion energy final. What was my fancy schmancy name for stored energy? What was my abbreviation for potential? PE. With symbols, we write this. PE initial plus, what was my abbreviation for motion energy? KE initial has to equal PE final plus KE final. And this has just, because it's a scalar, Christy, because it doesn't care about directions, this right there, that equation right there, opens up roller coaster analysis, because roller coasters change direction all the time. But if I know the height and if I know the speed, I can tell you an awful lot, and that's all I need. I said that wrong. I could have rhymed. Wow. All I need is the height and the speed. I could have done something like that. That would have been so much better. I could have made a little poetic thing. Oh, well, I missed out. If we want to be even more accurate, we can even include almost real world. You know, I often say in our magic physics world, make the numbers work out nice, and a few of you have said, are we ever going to do more accurate? We can be here. If the numbers don't add up, it's because in real life you always lose something to heat and sound. And so we could say this: the amount of potential you start with and the amount of kinetic you start with has to equal the amount of potential you end with and the amount of kinetic you end with. And if the numbers don't balance, Emma, whatever's left over must have gone into heat energy in joules. I'll put it in red so it stands out. Ooh, heat, hot. I think I have downloaded it here, Mr. Dewick. I hope. I'm looking for, yep. Skateboard parks are terrific examples of this. They're really good examples of this. So here is a skateboard park. If I lift this skateboarder up, what type of energy did I just give them? Gravitational potential, just potential for short. When I let go, what's going to happen? It's going to turn into kinetic. Now, if I put a little bar graph here, Emma, in the front row, you're the ones I'll pick on because you can see easier. So this goldish color here, can you read what it says there, Emma? Total energy. And what do you notice about that bar? It is not ever changing. That's the law of conservation of energy. The total energy that I gave this system was whatever I gave them when I lifted them up. But you'll notice that the potential and the kinetic are changing, and they're changing in equal quantities. When am I going to have maximum potential? At the top. So if I freeze it right there, not only should I have maximum potential, what's my kinetic? Which means, oh, since kinetic energy is a half mv squared, I've come to a stop. Because my mass hasn't gone to zero. What's gone to zero in that equation? The v. And yeah, you do come to a stop for a split second at the top. Where will I have maximum kinetic energy? The bottom? Okay. Now, this is magic physics world. And the reason it's magic physics world is I've turned off friction. In real life, your skate wheels and air resistance bleed off some energy. And so let's go to a more real-life example. Here is one where we have friction. I'm going to turn friction to near zero, but it's going to be still there. We'll turn the bar graph on, give the skater some potential energy. And now watch the difference. Notice one of the graphs is ever so slightly creeping higher. Again, Emma, can you read to me what that graph says? It's in red.
I can't see it, sorry.
Okay. Can you read it in red? Thermal, which is another word for a word being the letter H. Heat. Slowly we are losing, and by the way, this is our universe. This is why we are always having to add fuel or add more energy. Anytime we start a system going slowly, or quickly, depending on the efficiency, you're losing the energy to heat. Now, has the energy vanished? Has the total energy changed at all, Matteo? But you can see we have less and less left over for potential and kinetic. It's all gone into heat, and there's something called the Second Law of Thermodynamics. It's more complicated than what I'm about to say, but basically it says everything tends to chaos and disorder. That's what our universe is going to end up with. Our universe eventually, billions or maybe trillions of years from now, all of the energy, we're a massive ball of energy here on Earth. It will all spread out over the universe. It will all turn into heat, but when you run the numbers, the heat energy will be about 2 degrees Kelvin, which means the universe is just going to freeze and everything, all life will die. Previous coming attractions, I'm sorry, the universe will die someday. Okay? Who skateboards? You've been on a half pipe before? This is why you have to add energy every time. There's a certain point, and you practiced it, where you know if right now I push down with my legs and a little bit harder, what you're really doing is you're adding energy from your system, and that's how you can keep going up and down. But if you're bored sometime, just try remaining completely rigid, and you'll notice, oh yeah, I only went up and down a few times. This is not a very efficient system. Again, the other nice thing about this, Oliver, is because work and energy are scalars, if I was trying to analyze that curvy path with vectors, right here, What direction is the skateboarder traveling? Slanty. Ugh. We will look at slanties in Physics 12, and you're going to find, if you can do it with a scalar approach, much nicer. Okay? Is that all right? Back to the notes here. Oh, show marble energy transfer device. This is why I have that little toy behind me. Let me pause the video. A basketball is a great example, although you have to add energy to it. When the ball bounces, can you hear it? So that's wasted energy. You lose some energy to sound. And there is actually some heat generated. You may have noticed if you start with a cold basketball on the Saturday morning Egg McMuffin games and you start dribbling them, they do slowly heat up. So it's not a 100% efficient system, but at the top of the bounce, it's all gravitational potential. What's its speed at the top for a split second, Cole? No kinetic. At the bottom, how much kinetic energy, how much potential energy do you have on the ground? What's your height when you're on the ground as a number exactly? So how much potential energy do you have on the ground? Zero. It's all kinetic. When is it traveling faster? Fastest at the bottom. And you know this because you've dribbled, but there's the physics of why. Pile drivers are great examples as well. In a pile driver, we give it some potential energy. Pile driver, the industrial tool, not the wrestling move for those of you who are fans. And then what we do is we turn it into kinetic. Turn the page. A projectile is launched straight up into the air. If its initial velocity was 84.3 meters per second, how high does it go? Use energy. And we're going to ignore air friction and air resistance. Now, we could solve this Sierra by using d equals VIT plus a half AT squared and VF equals VI plus AT and VF squared equals VI squared plus 2AD. And the other one that I always forget. But we can also solve this with energy, and in particular, in part B, when I start trying to figure out how much energy was lost to air friction, that I can't do with our methods from before Christmas. See, I already picked on you, Sarah. Nick, what does this example 1A want me to find? So I guess I'm going to write H equals question mark. So, Nick, you know me enough to know that I like to try and give you a little first domino in your brain that you can tip over to get you thinking, when do I use conservation of energy? First of all, the question says to use energy, David, I know. But if there is a change in height, is there a change in height in this question, Nick?
Yeah.
If there is a change in speed, when I throw something in the air, does its speed change as it goes up? Yes. And then my third one is if there's a yucky, curvy path, that's definitely conservation of energy. Here, we're going straight up. We probably could solve this a different way, but conservation of energy will work. What's the law of conservation of energy? Can you read it to me from the first page, Nick? It had K's and P's and stuff like that in it. Mr. Duick. Yes, Nick. I said PE initial and then KE initial. You did KE first and then PE. Does the order when you're adding make a difference? Is 5 plus 4 the same as 4 plus 5? So I tend to flip-flop, and I've never found a pattern. It's whatever popped into my brain at the time. When you started to read it, I had already committed in my brain to writing KE, whatever. Now we always pause. Well, you know what? Let's do one more step. What was the equation for kinetic energy? Kinetic energy was a half m, and then I guess initial will be v initial squared? What was the equation for gravitational potential energy? That was mgh, and so Nick, I guess initial will have a little I right there? A half m v final squared plus m g h final. So I took the types of energy, Christy, from last day, and yeah, they're on your green sheet, and then I think I gave you this equation on your green sheet. Christy, I don't think I gave you the blue equation. I think I said I'm going to expect you to do the substitution yourself. Are any of these zero? When is potential energy 0? More specific, when we are on the... Are we starting out on the ground? So I either could have done that, or if I've been paying attention at the beginning, I could have crossed out PEI, because we know that's not a real province, right? Please. It's a little island. They call themselves a premier. They're a mayor, right? Let's be honest. You're not a premier. You're a mayor. You got a city. That's it. Now, kinetic energy will be 0 when it's stopped. Where will this projectile be stopped for a split second? So I could have crossed that out, or I'll cross that out. As you get good, you'll often cross stuff out on that first line, but the reason we're crossing it out is because V is 0 for a split second. And the reason we crossed out PEI is because H is 0. We get this. A half m V initial squared equals m g h final. Mr. Dueck. Yeah, Nick. They didn't give me the mass. Ooh. Wait a minute. Nick, is there an m right there?
Yeah.
Is there an m right there? Is there an m in everything? Well, then mass cancels. Because you would divide both sides by m, and it would vanish. Cole, one of these times I want to look and see your eyes open. Because I keep looking, and they're not. Nick, what are we trying to find? Oh! How would I get the H final? How would I get that by itself? We already canceled the m. That was convenient. Oh, you didn't even get me. Thank you. What was that saying? I was going to try and lead you to it, but you jumped there. Huh? You mean you have another equation that you don't need to memorize? Okay. So I'm going to write this then, Nick. The final height is going to be VI squared. You said divide by? Yep. And then that 1/2, that's like having a 2 there. There is also... Look up, don't write this down. Look up, don't write this down. A 1 there to get the 1/2. Will that 1 make a difference? So can I just never write it, please? Ever? That's extra writing, which to me, bleh. Okay. And you're okay, Nick, with where the 2 came from? It is on the bottom of the 1/2, so it ends up on the bottom with the G. Oh, here we go. 84.3 squared divided by 2 times 9.8, which is what? Three, 3482. Nick, is this a fraction? Say yes. Is there more than one thing on the bottom? Did you put brackets around the bottom? That's my guess. Because I think you seemed about 100 times too big, which means instead of dividing by 10, you multiplied by 10. There's my 100. What do you get? Anyone else? That sounds better. 362 meters, which is still pretty high. 362 or 3,620? 362? And meters. And now, finally, at least to a limited degree, I can take air resistance into account. Suppose the projectile only reaches a height of 72 meters instead of 300 and blah, blah, blah. How much energy did we lose to, we'll call it air friction, or if you want to say it another way, how much work did friction do, air friction do, slowing this projectile down? Brian, what does this question want me to find? How much? You know what? I think this is going to be a job for conservation of energy. So I'm going to write it out again. KE initial plus PE initial equals KE final plus PE final. But this time, Brian, because they're talking about friction and energy loss. That is heat. Are any of these 0? Prince Edward Island, because we're starting out on the ground. And at the top, how fast are we going for a split second? And that's what I meant by when you get good, you can sometimes cross these out without even doing the expansion. Brian, what am I trying to find? In this equation, what am I trying to find? Heat. How would I get the heat by itself? What's the PE final doing to the heat? Adding, subtracting, multiplying, or dividing? Adding. How will I move it over? No, really? That's nice. So you're telling me yet another equation. Please don't try and memorize all this. You're telling me what's going to drop down like a domino, the KE initial? And you're telling me I'll subtract the PE final? And then, Brian, do you mind, instead of writing equals heat, can I go heat equals? Can I put that on that side so it's by itself already? And this is also a nice review of some of the equation solving stuff we've done over the year. What was the equation for kinetic energy, Bri? So initial will be a half mv initial squared minus. What was the equation for potential energy? Gravitational potential energy. And since it's final, mgh. Yeah. Good. Brian, is there an m in this part right here? Is there an m in this term? Is there a letter m sitting there? This time the mass doesn't cancel. Because actually in real life, if I am accurate, it is tougher to launch heavier objects than lighter objects, and I've always kind of ignored that up until now. So we need a mass. Up here, let's make a little note. I'm just making this up. Let's make the mass 20 kilograms. Okay. How do I type a half on my calculator? So 0.5, 20. What was V initial? I've scrolled down. It was 80 something. 84.3. Don't forget the squared. Plus 20, 9.8. In a vacuum, in a vacuum, we would reach 300 and some meters. How many meters did we reach here? Which is way less. We lost a lot of energy to heat. I can tell you this object is not very aerodynamic. It's probably not shaped like a bowling ball. It's probably shaped... Did I miss? I don't know, because I'm dumb. Thank you. Rihanna got the candy first. She beat you to it, Cole. Good to see that you're awake, though. It's up to you, but I find I'm good enough on my calculator to type this entire line in all in one step. So I tend to... Is the calculator not opening? Let's try it again. There we go. It took a while. Boy, I was hitting that a bunch of times. I'm going to have a whole bunch of calculators opening now. So you can close. That was strange, and it's going to open one more time. I thought I hit it. Still got, okay, there we go. I find I can go 0.5 times 20 times 84.3. You all have a squared button and know where it is now, and you're starting to realize why certain buttons are there. They're used all the time in physics. And then take away 20 times 9.8 times 72. You can use your brackets for multiplication the way I hand wrote, but I find this is easier to read than brackets on my calculator. Brackets are always easier to read in my handwriting, not on my calculator. What do you get? It's going to be probably in the, this is a guess, tens of thousands, I think. At least in the thousands. I got something totally different. I got 69912.9. Mateo, am I wrong? Oh, you know what? The 9 didn't show up. I'm on a different planet. 9.8 is the Earth. 0.8, I'm on a little tiny asteroid with almost no gravity, which means I wouldn't lose much energy because I needed much energy in the first place. Is that better? 56.9, that there? So let's go, you know what, let's just call it 57,000. I'll go to 2 sig figs, but if you wrote the whole thing, that's fine. Brian, do you remember what the units are for heat? I'll give you a hint. It's a type of energy, so, joules. So this is the heat. But do me a favor, next to the word heat or after the 57,000 joules, this is also the work done by friction. The work done by friction. Christy, what does C want me to find? Of, keep reading. Now, normally, whenever I said friction, I would have said, hey, what's mu? And you would have said, I don't know, what's mu with you? Did they give me a mu or anything anywhere in this question? Anywhere, Christy? Say no, say no. Say. Okay, and the reason I'm doing this, we're now towards the end of the year. You have a whole bunch of different approaches you can pull from. And so my first thought would be, friction is what times what? Mu times an over. I don't see a mu anywhere. And wait. What did we find in part B? Also, you've had me long enough to know, Christy, that if it's a part C, the odds are it's going to use part B, so I would look back there. What did we find in part B? What else did I call that? The work done by? Ah. Now you ready to put everything together? Work is what times what? You can look. Okay. Did you hear everything that she said? Did she say force? Did you say force? Are they asking me to find a force? And you said force? Okay. See kind of where we're going? Let's try writing that down. So you just said work equals force times distance. But now I'm going to specialize. The work done by friction would be the force of friction times the distance that friction was acting. Brian, what is the distance that friction was acting for? 7. Ah! The height. Christy, first of all, how would I get the force by itself? What's the D doing to the F? Adding, subtracting, multiplying, or dividing? And so you're going to? So yet another way to calculate friction from energy this time. Please don't memorize it. You're telling me that I can find the force of friction by taking my answer. I'm going to write 57,000. But you know what am I going to use on my calculator? My answer button. And Brian, what did you say that the distance that the friction was acting for was? In fact, we've called that a height. And so now we're able to find an average air friction force without having to pull calculus out, without having to pull all... This is nice, actually. What'd you get? It's a force, Christy. What are the units for force? Yep. 791 newtons. I don't know of any easy way without calculus, aside from conservation of energy, to do that. Mr. Dewick has a very cool demonstration. I have a car accident simulator. Back up. When do I use the conservation of energy, Nick? I alluded to this earlier. When there's a change in height, when there's a change in speed, I can use it then, although it might not be the fastest method, but especially if there is a yucky, curvy path. Skiing and roller coasters are two of the great ones. So, at location Z, a skier is traveling at 18 meters per second. How high up the next slope can the skier reach? And let's ignore friction, because snow is pretty good. Nearly frictionless. Tristan, what's this question asking me to find? Height. Is there a change in height?
So yes.
As they go up the hill, will there be a change in speed? Is there a yucky, curvy path? This is a job for conservation of energy. And what's that? It says this. Kinetic initial plus potential initial equals kinetic final plus potential final. Are any of these 0? There's 2 potentials. I need more specific. Oh, initial, because we're on the ground. PEI again. Yeah, they're mayor, not a province. Huh? There's 2 kinetics. Which one? Oh, you're saying if I want maximum height at the top, just like on the skate park, I'll come to a stop for a split second. So you're saying I can do that? Oh, that's nice. So if you can't remember, by the way, if you want to, you can put a little equals 0, so that when you're studying later on, you know why we crossed them out. Tristan, what was the equation for kinetic energy? It's on your sheet there. It's a half something, something, something.
Half mv squared.
Oh, I like that. What was, oh, and this will be, since it's kinetic initial, V initial squared, yes? Equals. And what was the equation for potential energy? Really, I should be saying gravitational potential energy, but potential energy? Nice. Now, in this question, I gave you the mass, and you would get full marks if you included it, but is there an m in every single term? Let's be lazy then and say, yay. Do you see why that is? Because if you divide one side by m, you'll get m over m on the other side. What's 5 divided by 5? 1. What's 10 divided by 10? 1. What's m divided by m? 1. Will multiplying by 1 change anything? That's really what I mean by, we can save ourselves some time, the m cancels. It won't cancel if there's heat. It will cancel at other times. What are we trying to find? You'll notice we get the same equation that Nick derived. How would I get the h by itself, Tristan? More specific. Yeah. So Nick, we could almost name this after Nick. Maybe we should. Nick's theorem. He said it was VI squared. And then I wrote it like that because that was prettier. You could put a 1/2 VI squared G or a 0.5 times, but that looks to me prettier. Finish it off, Tristan. What was VI? Okay. And by the way, if we weren't using a scalar approach, you see, because the initial velocity is in that direction and the final height is in that direction, normally we could not do this. If this was a vector approach, we cannot combine those. But because energy is a scalar, it lets us handle yucky, curvy paths. So what was it, 18? Don't forget the squared. Divided by 2. And then 9.8. Nick, is there a fraction?
Yeah.
Is there more than one thing on the bottom? Okay, just saying. This is really close to 20 squared divided by 20. The answer is going to be really close to 20, I think. Double check me, but it's like 17, 18. 16.5? Go. Speed, units. No, height, meters. Right? Turn the page. How many more are we doing? 1, 2. I got a big one coming up. I don't know if we're quite going to get through all this today. We'll see. Bow and arrow, is that what we're on now? Okay. This is also an example of conservation of energy. Only this time the potential is not because of gravity. It's not mgh. It's because of the elastic energy we're storing in the bow. Because of that. So, let's dive in. Emily, what does A want me to find? Work. Well, I know that work is force times distance. And I guess the force is going to be the force in pulling the bow. How big? Yeah. By the way, the reason I think I said this the other day, but I'll say it again. The reason I said average is if you ever have used a compound bow, the force is not constant. It turns out tough and it gets easier the further you pull it. It's using pulleys and stuff like that. But we'll just use an average. 245, what was the distance? So fix that. We don't do centimeters. Yep. How many joules of energy are stored? How much work did I do? How many joules of energy are stored in the bow? Oh, I like example 3. I like example 3. Example 3 is a nice question. I like example 3. I like example 3. I get 245 times 0.68 Do you get 166.6? You could write 167, but I'll write this down. Emily, what does B want me to find?
Potential energy.
How much potential energy is stored in the bow? Not MGH, because this is not potential energy done by lifting an object. What's the correct answer here? Same answer. That it's now stored. When I let go, what happens to that energy? It gets turned into on which object? Yeah. And so what am I asking you to find in part C? This is a job for conservation of energy. We're going to say this. Potential initial, kinetic initial, potential final, plus kinetic final. What's the initial speed of the arrow? So I can do that. What's the final potential energy stored in the bow after you let go of the string? I can do that. This time it's not because of MGH, it's because of, you know what? All the energy got transferred. And really what we're saying is that 166.6 gets turned into kinetic. We can say 166.6 equals, what was the equation for kinetic energy? I'd like to get the V by itself. How? Well, I'm going to do with the M. And then I'm going to ignore the 1. What am I going to do with this 2 on the bottom here? Oh, so you're telling me 2 times 166.6 divided by, is that right? 42? Is that right? Why not? Grams? Isn't 0.42? No. 0.042, because kilograms is out of 1,000. Now that gives me V squared. Oh, square root, you say? So this allows us to calculate how fast an arrow would leave a bow. Times by 2, divide by 0.042, square root. What do we get? Does that seem right? I've seen bows fired in real life, 89 meters per second. That's about the length of the football field, the soccer field behind me in 1 second. That's about right, because I watch them. I can move my eyes and follow them, but they're going really fast. So, yeah, about the football field in 1 second, that seems okay to me. Ballpark, I'm good with that. My Nerf dart gun works very similarly. I go like this. Work equals force times distance. There's the force and the distance. I've just stored energy in here. When I pull the trigger, what does the energy get transformed into? Kinetic. The only problem is I've actually analyzed this. This is going to jam. Let me get one lined up here. See if this will work. I've analyzed how fast it should be coming out by calculate. I've actually measured the force, measured the distance, and then done this same question and solved for V. And then we've used a radar gun to measure it. This is about 5% efficient. We lose a lot of energy to heat and noise and sound. It should be coming out way faster. Well, I've also heard you can take these apart and soup them up pretty dramatically if you look at online instructions. Next class, we're going to mark the take-home quiz, and we'll finish this lesson. But if you want to get a head start on the homework, you can try already question number 1. Now, question number 1, I need to introduce a new term. So can you find question number 1? This is the skate park. ME, mechanical energy, that's potential plus kinetic. That's the gold bar total energy that we were looking at in our skate park situation. So you can figure out right now how much kinetic energy you have by going a half mv squared. How much potential energy do we have at location 1? 0. And so me is going to be add those two. Me is going to be add those two. Me is going to be add those two. But you can figure out how fast you're going to be traveling or the missing stuff at these heights. If you're not sure, I'll help you with this more on Monday. So you can try number 1. You can try number 2, roller coaster. You can try number 3, but your first job is to get the take-home quiz done.